Good afternoon and welcome to the Zero Emission Buildings Academy. I'm Quentin de Hulst, the Director of Green and Healthy Buildings at the European Copper Institute. We organize this series of webinars in partnership with the Building Performance Institute Europe, BPIE, and the European Construction Technology Platform, ECTP. We promote the transition to a zero-emission building stock. It's a climate policy objective of the EU, bringing multiple benefits. But its implementation of this necessary renovation wave requires action at all levels of the political governance and of the value chain. And to have action, we also need to have exchange of information. And that's the idea of this academy, to share knowledge. So each webinar invites one or more experts to deep dive on one specific aspect that is relevant for this transition of the building stock. And we pay attention to have enough time for questions during each webinar as well. So today we have two speakers. We will deep dive on the topic of recovered energy. We often speak about energy efficiency and renewables as being the two key pillars and mantras of the energy performance of buildings. But there is also potential to recover energy from ventilation and wastewater, for example. And that's where we will focus today. The first speaker, Pavel Sevela from the University of Innsbruck, will present about the potential to recover energy from wastewater. And the second speaker, Laurent Sokal from the Energy Performance of Building Center, will speak about the integration of recovery into the EPB standards, so for the calculation of the energy performance of buildings. So we will start with the two presentations and then come to your questions at the end. So as a reminder, don't hesitate to put questions into the Q&A menu. And now I will give the floor to Pavel for his presentation about the potential of wastewater heat recovery.
Yeah, so thank you very much for the invitation. It's a pleasure to be here and to present our findings of the study we wrote last year, actually. So I'd like to share my screen now. I assume that you can see my slides. If not, please write into the chat.
Yes, it's going well.
Thank you. Great. As already said, this presentation is based on a study called The Potential of Wastewater Heat Recovery Systems, introducing the energy need for water heating in the EU in a cost-efficient way. We wrote this study together with the University of Innsbruck and Passive Institute, and the study was commissioned by ECI. So let me begin. The facts you probably already heard of is that the energy sector delivers 40% just for running of the building. So the building sector is actually the greatest consumer on its own, and emits about 36% of the European CO2 emissions only on the operation of the building. So the construction of the buildings is not included. To sensibilize the topic of the hot water, I found out that about 22 million cubic meters of hot water flows down into the drain out of the European households. And this is a number which is coming daily. Where this hot water comes from, 70 to 82% can be tracked up to the showers. So it's a very actual topic, and this is why we started the research work in this field. As we see here on this chart on the right side, this is actually the forecast for reducing the energy consumption in the European Union all the way down to 2030, so-called the Fit for 55 energy targets. As you see, between years 1990 until current state, the energy need and the energy consumption for the space heating actually have been drastically reduced because of the strength regulations on the from the EU, such as insulation of the building envelope, better glazing in the windows, and so on. But there is not much happening in the small arrows. It's the hot water consumption. And surprisingly, there is also not much expectation from the energy savings in the hot water sector. And I hope this presentation and this webinar will change your mind on that topic. The truth is that at the general mix of the building sector in European Union nowadays shows about 15% of the final energy on the hot water consumption. But this is actually the true for the average of the building sector. The situation looks drastically different if you have a look of the newly building houses, such as this one in Innsbruck in 2010, so already 13 years ago. The building, of course, it's in a passive standard in this case, but already back then we can see that the domestic hot water energy consumption surpassed the space heating. This is actually why we have to focus on hot water, because it seems to be that the sewer might be the very last thermal bridge in the building envelope. We have not really seen, maybe because it's really under the ground and we can't really see it. Okay, so when we speak about the hot water consumption, there is a lot of buzzwords regarding energy need and energy consumption. I would like to distinguish between those two. The energy need in this case means actually the amount of energy delivered by the water into your use. So in this case, for example, the shower, the number of liters on a certain temperature that is actually heated up from the groundwater temperature. But this is not the full story, right? There is also this so-called the delivered energy, which includes also the inefficiencies of the hot water system. So let's say you have a central system with circulation losses, so and storage losses, and also the heater itself. It doesn't have 100% efficiency. So if we talk about 100% of the energy which is delivered into the building to make the hot water system function, we can roughly say that about 30 to 50% is lost in the storage and circulation system itself, and about 50 to 70% actually goes down to the drain. So it seems like a not very efficient way of using energy, which is most of the time fossil fuels in Europe. And this is why the wastewater heat recovery makes such a big difference. In this perspective, we cannot, of course, do anything with the efficiency of the hot water system on its own. So let's say this 30 to 50%, we can't influence, but this 50 to 70% is the rest we can still address through with this so-called wastewater heat recovery technology. And why showers? Why we all the time raise this topic? Because the showers are really the majority of the hot water application, and it's also the longest process in the households. The average shower takes about 5 to 8 minutes. It's rough to say, but it's very person specific. The average flow rate is about 8 to 9 liters, and based on location on the globe, of course, and the groundwater temperature. So you need to heat up the water, you need about 1.4 kilowatt hours per every shower cycle in that case. All the other hot water applications in a household are either very insignificant or very short. So the application of the wastewater heat recovery might be not very efficient in this case. Each of you probably already heard about wastewater heat recovery or know some of the products which are there on the market. They are actually just 3 levels of the so-called wastewater heat recovery. The biggest one, so let's say the sewage system in the city level, is something that is very well combinable with 2 other levels, so-called in-building, either central. So this means on the here on the building level, so there is one heat recovery unit which serves for the all flats, or there is a decentralized system which is basically either a drain or a pipe in a shaft, which is serving 1 or 2 showers or baths, which are very close to each other. In this presentation and the study, we focus on decentralized units because they are the most efficient and they proved themselves over more than a decade as a functional system, bring very good efficiency and economy. This is how the decentralized heat exchangers might look like. On the left side, you see so-called tube in a tube, or a pipe in a pipe heat exchanger, where the drain water flows inside. The drain water is attached to the inner copper heat exchanger through the Conda effect. And in the outer pocket flows the cold water in other direction. And that's where actually the heat exchange happens. This pipe must be always installed in a vertical way. There are also drains, which are directly installed into the floor in the showers, or there are some kind of combinations where you have a pipes with the pumps, so-called active systems. There are at least 20 plus companies in Europe producing and manufacturing a wastewater heat recovery system in Europe. So the market is already booming. And now, actually, how these heat exchangers might be connected into your hot water system in the building. There are three ways. There are three charts how these heat exchangers might be connected. I start with the most efficient one, the so-called scheme A. This describes a situation where the heat exchanger, doesn't matter what type of heat exchanger it is connected firstly to the cold water side of the mixer, and secondary, it feeds the heater its own. In this case, all the water that goes through the heat exchanger reaches also the shower head. So once through the mixer, so you need to mix less hot water, because the cold water, instead of having, let's say, 10 degrees, thanks to the heat exchanger, is heated up to, let's say, 30 degrees. So you take less heat and hot water from the hot water tank or heater. And secondary, because the heater itself is fed by preheated water, it has to work less. So you save also, I mean, this is the main energy saving actually, because you actually don't heat as much hot water as you would without wastewater heat recovery. This is also called a balanced volume flow rate, because on the primary and the secondary side of the heat exchanger happens actually the very same volume flow rates. And this is the most efficient way how the heat exchanger is actually connected into your HVAC scheme. There exists also two other ways, the scheme B and C, where the preheated water is either often the case by the drains in a shower, or the preheated water is actually fed into the heater. This is most of the time case in central systems, because hydraulically it would be very difficult to do it otherwise. But if you're a planner or a craftsman and you think about using the wastewater heat recovery, try to always rethink the scheme of the hot water system and use the scheme A, because you will get the most energy back out of the same heat exchanger for the same value. If we jump up from the building level to, let's say, the Europe level, we will see that in our study, we divided European Union into four climate zones. And we demonstrated on 3 different hot water systems, once in a heat pump system in a central level, then decentral electric hot water storage tanks, and third is basically fossil fuel hot water system, or heating system, also on a central level. And we had a look what happens if we apply this pipe and a pipe heat exchangers on a decentralized level in a multifamily building in these 4 climate zones. Based on the cold water temperature in the ground, which is obviously colder in the north and the south, the energy need, so basically the kilowatt hours we need to spend on delivering the hot water for the user will be higher, of course, in the north. In this case, we see what is the proportion of the savings delivered by the heat exchangers. It varies between 33 to 36, let's say 1/3 energy could be recovered. But what is actually more important for you is the energy demand. So the the delivered energy. So it's actually the amount of electricity, gas, or whatever you use as a fuel in the building. You might see more details in the study itself, but I can say that, of course, the difference between the energy need and delivered energy is in the efficiency or inefficiency of the hot water system itself. So let's say for the heat pump in an oceanic climate or continental, which is basically, let's say, Germany. So the COP of the heat pump, so let's say the high efficiency, reduces the economy of the wastewater heat recovery system because it's already so efficient. And on the other way, in the fossil fuel systems, which are very inefficient, the only saving measure, which is the wastewater heat recovery, has a higher impact. Also, a quite interesting figure could be seen here, where we compared the actual technology mix for hot water production of every member states of European Union and combine it with the CO2 mix for every nation based on how the electricity or if it's a gas heating is produced and where it's coming from. And we would see here what is actually the impact of installing one heat exchanger on which is being saved, respects, of course, the climate zone. So let's say in the Nordic countries is the energy saving potential higher than in the South. But this doesn't really represent, or there is actually no connection between CO2 savings, because some countries are very much fossil fuels based. So the application of the wastewater heat recovery brings a lot in terms of ecology, even though it might be less interesting in the terms of saving energy as in Nordic countries. So let's say in Greece, you save as much CO2 as in Germany, even though the climate is very much colder in Germany than in Greece. Further, we also had a look at what would happen if we look into the future. In the year 2030, the nearly zero energy buildings should be replaced by so-called nearly zero emission buildings. If you never heard about it, it's about primary energy, which is being delivered into the building and depends on the member state, which defines its own regulation. It's varies somewhere between 20 to 50 kilowatt hours per square meter primary energy. So this is a very, very strict energy standard, which is coming up in 7 years. And we had a look what would happen with such a single family house of 4 people if the heat recovery system, again, the pipe in a pipe, is being installed. So let's say how much easier it would be to reach the energy standard with the wastewater heat recovery system. So on the chart on the right side, you see that it makes about 7 kilowatt hours per square meter and year of the primary energy. So it is a significant contribution. It's about 13% of the total delivered energy balance into the building. So if the let's say the planning gets harder and harder, it seems to be that without wastewater heat recovery, it would be very difficult to reach the strict limits of, let's say, 40 kilowatt hours per square meter in the year, because also this the auxiliary energy for lighting and other electricity applications are included into this balance. Probably everybody of you is interested in the economy of such a systems, right? As I expect. We used for evaluating the economy, the method of so-called cost of the saved energy. What does it mean? So we don't tell you what is the payback time because it very much depends. But instead, we decided to do for these 4 climates, this cost of saved energy. So basically, we take the price of the product, let's say of the heat exchanger, And we say it functions for, let's say, 25 years because it's just a tube. So it has the same lifetime as the general piping in your building. And we know how much energy can be saved for this average European household. We divide it by the 25 years. So we know that the amount of energy over this 25 years that cost you 25 years ago, let's say, this certain amount to be bought and installed in your building, distributed is, let's say, in the continental climate, 0.08. So you can see also the way that this is actually the fixed energy price for the next 25 years for your energy delivery. So 8 cents is quite little comparing to the actual energy prices. I think Germany is about 30 cents per kilowatt hour. So with the wastewater heat recovery installed today, you will have every kilowatt hour delivered by the heat exchanger for 8 cents. So this is another way how to get less vulnerable to the changing prices on the market. And the last chart of the study, which I would like to present to you, is what is actually the impact on the European level if we would apply the wastewater heat recovery on the upcoming 35 million renovations and 15 million newly built units between the year 22 and 30. These numbers comes from the Renovave and the prediction of European Commission, what will be the building sector behaving about. We said that this roughly 50 million buildings which are being erected or renovated in the next 8 years will adopt the wastewater heat recovery in either 20, 50, 80, or let's say 100% of all of the buildings which are being additionally renovated or built to the residential sector which is existing. And we see that we actually can totally compensate the increasing energy consumption of the building sector in this field. Or if we would be able to apply the wastewater heat recovery to all the existing buildings on a whole market, we would surplus the EU energy targets set for 2030. So the application of the wastewater heat recovery systems might be very useful if somebody from European Commission, for example, listening right now. We are coming back to conclusions, and I would like to actually read this quote because it's very accurate from Jürgen Schnieders. As a passive system with no moving parts and no maintenance and lifespan as long as the water pipe system itself, this is a unique feature for the energy saving technology without loss of the comfort. So that's a rough definition of what wastewater heat recovery actually is. About 40% of the delivered energy can be saved if the domestic water system is optimized. This means the distribution and storage losses are minimized as possible. I'm sorry for reading the comments, but the presentation will be also shared on its own. Yes, the economy is particularly good in, of course, applications where multiple users are using it. So let's say sport facilities, hotels, businesses. For a family, it means more than 100 euros per year. And of course, the economy is increasingly better in climates with a colder water or let's say winter. So either Nordic countries. Let's say the CO2 savings or the ecological footprint of the heat exchanger is balanced approximately already during the first year. This is quite typical that the economy payback time is a bit longer than the ecological. And the heat exchangers are very easy to recycle because they're mostly made of plastic and copper, and shows a lifespan for more than 20 years. And it's all without moving parts. This is also an interesting way how to have a look on the decarbonization of the building sector in Europe, which is actually having just current renovation rate of 1%. because the HVAC shows about 3 times higher renovation rate. So applying the wastewater heat recovery systems on a European level can cause more rapid reduction of the CO2 and reaching energy savings than investing only into, let's say, the building envelope renovation. And as we see, the wastewater heat recovery can also exceed the European targets we just set for hot water energy reduction by 24% and 1,000 terawatt hours per year, without actually using the comfort of people taking the showers. What we actually need to do now is create European norms and also eco-design directives for the wastewater heat recovery, which is currently missing. We might discuss it further in the discussion because there are already some action being taken, and this would be very useful if the wastewater heat recovery could be included in the EU toolbox, as said already before. And what we really need now is to train the professionals, the craftsmen, the planners, the architects, how actually the system could be planned in a renovation or in newly built houses, so the technology gets onto the market much faster. If you're interested to hear or read more on the study, you can find the full paper. I can also copy the links into the chat. Or if you have less time, there is also a shorter version of having just 8 pages with a lot of graphics under this link. And last but not least, I would like to show you a very interesting video, which is being taken in the fair ISH in Frankfurt this year, showing a heat exchanger. I think it's playing. So here's the heat exchanger from the company Julia. And you see actually the projection of the actual temperature on the shower tray. Right now, the heat recovery has been switched on. So you see the temperature of the water after the heat exchanger is cooling down because the heat recovery works. And the heat, instead of going to the drain, is transformed into the preheated water. And that's why actually the temperature on a shower head is increasing. So simple.
Thank you, Pavel, for
attention.
This presentation and clear demonstration of the interest of recovering energy, and then particularly on wastewater. The next question that comes to it is how to integrate this into the energy performance of buildings calculation. And that's where I would like to give the floor to Laurent to guide us in the world of EPB standards and the consideration of recovered energy.
Okay, thank you. Good afternoon, everybody. Thank you for the invitation. So now we will speak a little bit about the integration into the EPB standard calculations. So here, and I have to share my screen. And I hope you can see my screen with the presentation now.
Yes, we can.
Okay, that's okay. So the context now is that the modern civilization and well-being is based on the massive availability. This is an objective we should remember, and use of quite a lot of cheap energy. But there is a concern about sustainability because of an environmental impact. That's why we are turning to zero emission buildings, which is the next target, and also in depleting resources to get this energy. That's why we had a nearly zero energy building up to now in our regulation, and also some other concerns like dependency from some suppliers. And now we are planning a tough transition. So we need all available tools, including wastewater heat recovery, but we have to integrate this into the context. Why it's important, Pavel already mentioned why. Because we are concerned in EPBD, the energy performance of building directives deals with the energy which is used to provide comfort services, that is making our buildings habitable. And we have to provide a number of services. Here you have the list: heating, cooling, domestic hot water, ventilation. And here, a very quick and dirty and very subjective estimation of how much they impact in kilowatt-hour per square meter per year. Of course, it depends on the age of the building. It depends on your location. But until now, the top consumer was heating. But now we are killing heating needs by insulating buildings, which is, of course, reasonable. So all the other details are starting to appear, including domestic hot water. That's why we are moving to consider wastewater heat recovery. And it's not only a question of needs, because we have to provide needs, but to do this, we are using technical systems which have losses, use auxiliary energy, so they have an efficiency, and they generate what we call delivered energy. And now we are starting also to export something, just to make things a little bit more complicated. And this is not the end of the story, because depending on the energy carrier, you're using certain resources. So the actual result, which is interesting, is in terms of weighted energy. So primary energy, non-renewable, or renewable, or total, or CO2 emission, and even cost. Please remember the adjective I used before, or the term, sustainability includes all these aspects, so that we can continue providing services and also production and transport. So in these schematics, it's important to have a clear definition, because when we speak about needs, we are just on the theoretical amount of energy required, but then we need some usable energy provided by the generation subsystem, which will ask from the exterior, from the environment. They will ask for delivered energy as an energy carrier amount. So it could be gas, electricity, heat from district heating, and the final impact is in terms of weighted energy. So we have to remember all these terms to be very clear, because it's always kilowatt hours or kilowatt hour per square meter, but it can mean something quite different. And if we want to obtain sustainable buildings, which is what we need, what we want to reach at the end, you have to act on all these, on the whole story of the process of using energy in a building. So you have to reduce needs. So this is done per service, and the first could be user behavior, moderation. And for heating, we can insulate, optimize gains. For lighting, you can optimize daylight. For cooling, you can provide shadings. But domestic hot water, you can't do anything about reducing needs, or probably you can have some user moderation. But since this is a very user-specific service, then you can reduce delivered energy. So you build efficient systems, and here you have a bunch of solutions for this. Main one, control service emission, how much, when, where, reduce losses, all these things. And when you select generation system, you allow the use of energy carrier from sustainable resources. This is the last step. That's why, for example, we are moving to heat pumps now. You can change technology, combustion to go to heat pumps, or for example, for lighting from incandescence to LED. And at the end, you try to use sustainable resources if your generation system enables you to do that. So you can use photovoltaic, thermal solar, hydropower through the electric grid, of course, or use low carbon emission sources, which is often similar, but not really the same as using renewable. And third, you could also recover, recycle energy, regeneration. We will come back on this topic shortly after this. And of course, if you want to set up legal requirements and you want to improve, you need a meter. You can't improve anything, nor regulate it, if you can't measure it. Lord Kelvin was about improving, but also regulation. Why? Because if you want to set a limit, a target with a regulation, you need a meter that allows to meter what is the performance of your building. That's the synergy which is needed between the calculation standards, particularly EN standards, and in this case, on the European level, it will be EN standards and the APBD directive. If it is going to fix some values, then you need a correct meter. Because if you change the meter, of course, the value will have the numeric value, the figure will have a different meaning. And that's why that's why the Commission financed in the past the provision of so-called EN EPB standard. EN standards concerning the energy performance of buildings, because we have several national meters, all different. So there has been a first drafting in 2007 and a revision in 2017 under 2 mandates, and now we are in the periodic review of these standards. That's why wastewater heat recovery, which is for now missing here, will be included shortly. And just to have a small flavor, this is the EPB calculation scheme. It looks very complicated, of course, because you have to deal with a lot of things, a lot of services, a lot of type of generations, a lot of type of technical systems, and probably people complain a lot, but maybe standards are complicated just because buildings are becoming more and more complicated with all these systems. So we have to do it by modules, such a complicated calculation, a mainframe and specific modules for each technology. And that's a complete picture for the EN EPB standards. Here you have the standards and actually the modules that concern the operating conditions or the climate, so the boundary conditions. You have standards about the heating and cooling needs, EN ISO 52016, and of course, all modules for all type of technical systems for all levels within technical system, which are more or less roughly the same for all services, plus domestic hot water, lighting, and then the conversion to primary energy. So we don't need to remember all these details. I will give you a source of information for this in a short time. What is a module? Of course, to do all this calculation, each module is a package covering a specific topic. So a technology, you have an EN standard, which is a calculation procedure drafted according rules that allow to use them easily, a send technical report to explain the reason for all the calculation procedure, an accompanying Excel sheet to demonstrate the calculation procedure, and internally there is a quality checklist to verify if we comply to this. This is an example of how it works, because you, of course, you have the module which is a mainframe of the calculation. In this case, this is an EN module, and a lot of modules for all your technology. So you have here product data and other local data that goes into the module for your technology. And of course, you have a well-defined in and out structure, so that if you like, you could even take the EN structure and connect a national module, provided your input and output is compatible. But since it is documented, this is okay. And as well, you could use into your national scheme an EN module. So if there is a EN module for wastewater heat recovery, this could be connected to national calculation schemes. Up to now, there was not the obligation to have a common calculation scheme all around Europe. You have to take into account some things, but each country typically has its own national scheme. But as it is designed, the national schemes are not so far away, and you can pick and use some module if you like. And if you want more information about EN EPB standards, you can go to EPB Center website. Here you have the link, and you have different features. You have short videos, 10-15 minutes each, which is for basic information. You have webinars, 1 hour each, which is, I would say, an intermediate level. And then you have case studies, including the supporting XLRs with all the calculation demonstrated in hourly calculations. This is more for advanced users. And basic, of course, there is one, a simplified case study about EN ISO 52000-1, which is quite interesting about imported and exported energy, and plus a lot of documents. So just feel free to go there, and all the material is downloadable. And you will have much more details on what I've had to tell you very quickly until now. Why the interest in wastewater heat recovery? This has already been expressed, and when trying to be efficient, you can act on systems, so we can improve system efficiency, since we cannot reduce more or less domestic hot water needs. So you can act on system efficiency. You can use renewable energy, for example, thermal solar or PV with a heat pump, or you could regenerate energy. This is the idea of using wastewater heat recovery when showering. Why regenerating? Just shortly, because you are reusing the same energy several times. So you have to provide the hot water, and then this hot water will cool down in the drain. But if you can capture this heat and heat the incoming water, then you can reuse this. Theoretically and ideally, once you launch a system, if you had a perfect heat exchanger, you could keep showering or the same ventilating your house without any loss, as long as you want. But of course, there are some things that are non-ideal and that prevent us to get to the full result, and that's quite normal. So there is a strong interest. Well, level playing field. What does this mean? It means that if you want to take into account a technology, all technology should be considered. So if you want a technology, to contribute to the energy performance, this technology must be available, and it is. It is known by professionals and users. It's not really the case all around Europe. It should be mentioned in the regulation, so it should be mentioned in the PBD directive, and then it should be taken into account in the calculation procedure. So the question is, are there national calculation modules, or is there an EPB standards module for wastewater heat recovery? And if we look at the current wastewater heat recovery calculation, you can find this calculation in several countries. Here you have a number. I think there is also Germany to be included. But you can see that here you have different aspects of the calculation procedure. If it is defined, which is a fraction of needs for shower, and all these aspects, and you can see that the result for all countries is quite different. So it's really, every country has differences, not to mention the source of product data. Here is various, here they have their own testing standard. This is also another barrier for the use of this product and the valorization inside the energy performance of buildings. So that's why a new calculation module for wastewater heat recovery is going to be is under production. And as an information, there are the basic calculation steps of the recovered fraction of the energy needs for domestic hot water, and these are the potential impacts. So the share of needs for showering, not everything is for showering, so roughly 80%. Then you have unavoidable losses because water cools down in the shower basin. So this is 15 to 20%, which is lost, not available. Then you have the maximum recoverable heat due to the connection. Pavel already mentioned connection type A, B, and C, and this could be a 1 to a 0 event. So that's very important to know how to use and correctly this device. Then you have the recovered fraction of recoverable heat due to heat exchanger efficiency. So here it's where the heat efficiency of the heat exchanger is coming into play. And this, you have differences between counterflow, of course, or something very simple, quick and very fast. And you have also transient operation, which does something, plus some details. And the new model, this new module taking into calculation module, taking into account all these aspects, will be available on the APB Center website in a small number of weeks, let's say. And here I will go fast on this because time is running. And here you can see some figures about the operation. This is type A connection, which is a more efficient. And by the way, that's why A is very important because it keeps a 1 here, whilst B and C could go down. So here you have type A connections and just an example of the operating condition, and you can still recover nearly half of the total domestic hot water needs with this. And the equation are quite simple. On type B and C connections, the issue is that not all the flow rate of the hot water in the shower, which goes down to the drain, and on the drain side you go through the device, only partly goes to the heat recovery. So this limits the flow rate, and this limits the amount of energy you can recover. And for type B, obviously, if you decrease this setup temperature, this will reduce the water that you have to take from the cold water line to obtain the 40 degrees. That's why type B connection is depending on the set point temperature here. And this is the equation to calculate this effect. And the same is true for type C connection. When you change this setup temperature, this changes also the amount of domestic hot water that goes through this line. Ideally, if you have 40 degrees and here you set 40 degrees, all the water will come from here, so you can recover everything. But then you will lose something if you increase this temperature. So in short, if you want to see the effect, here you have the maximum recoverable percentage of needs. And we lose something because the water is cooling down in the shower cabin, but then with connection A, we can recover all the rest. With C, you have this maximum recovery, and type B depends on the efficiency of your heat exchanger. And here it is the set point. The driving variable is the set point of your domestic hot water heater. That's why I mentioned it's important not only the connection, but also the setup of your installation. So the set temperature for your domestic hot water preparation. And that brings in also another question, very important. It is also to commission your system so that you maximize the efficiency of your system during actual utilization. And the calculation to take into account all these kind of things is quite simple, maybe more or less 5 simple equations and no special data required. So it's quite easy. Transient operation, that's the concept, is that when you close a tap, water is trapped here, and this, even if it was heat recovered, then it will be lost to the environment. And that's more or less a 10% effect with the normal timing of the use of a shower. Renewable, recoverable. And to conclude this presentation, just a couple of words about the terminology, which is very important. One problem is also that sometimes the regulation is based on definitions which are a little bit partial or not really to the point, and this could create a barrier. And for example, very often you have requirements in member states about the renewable energy ratio. For example, in Italy, you need half of that. But of course, wastewater heat recovery has an effect which is quite similar to using renewable energy, but it's not renewable energy. So you have a hidden technological barrier to this. And this is something we should avoid. Actually, wastewater heat recovery does not reduce energy needs. It contributes to covering energy needs with regenerated energy, which is no less sustainable than renewable energy. So that's why we should adapt all things around so that this technology could be correctly evaluated. And of course, you should not mix. And these are some examples that I leave to you to read because, for example, efficient only means get more, pay less. So it qualifies a technical system. Renewable, you don't exhaust resources at the given rate of exploitation. It will always be available. This means eternal, and it qualifies a resource. Sustainable means it's possible to continue to perform it indefinitely at a foreseen rate without any issue, including environment, social, and economic aspects. And this qualifies an entire process of provide comfort services in a building. So this is a real goal that we have to aim to. And these are means to reach this goal. And also you should not mix heat loss reduction, heat loss recovery, because heat loss is just heat that is deviating from the intended destination. Recovery, it is heat that is lost by the system, but still useful despite the deviation. And heat regeneration is that you transfer heat from one side to another of a cyclic process. In this case, we are heating and then cooling the domestic hot water. So if we can transfer heat from the cooling to the heating, we can regenerate this energy. And probably if you remember your studies in thermodynamics, feed water preheat with steam extraction from a turbine is an example of regeneration. And it's the same when you have heating incoming domestic hot water with outflowing drain water, or heating or cooling incoming outdoor air with expelled exhaust air. We are actually regenerating energy, recycling. And for an ideal heating process, regeneration could supply the entire needs of heating. Of course, we have some limitation as well. So I think this is just a repetition. So I will skip this slide and it will be available for you to read. So we must be very careful with definition, and we should focus on principles only. And otherwise, if you use specific case or provide detail, you will limit emerging technology. And for example, it's always funny to read zero emission building. Emission is a building with a very high energy performance. So it should be something linked to emission if this is the goal. Okay, so keep in mind this hierarchy. And here again, I will let this for you to read because I've already expressed the concepts. So we need calculation methods, and it's not only the module for the specific technology, it's also we must be aware of nearly hidden parameters. And for example, quite an interesting example is in EN ISO 52000-1, the K exported, which qualified exported energy, is really a game changer. And we see the short video on APB Center website explaining this. But as well, dealing with renewable and regeneration, how to consider both if you ask for an indicator of the share of sustainable energy. And here we have a short example. You have your energy need, for example, for domestic hot water, and suppose that you are covering 50% with your recovered energy, your technical system output is 50, you have 20 losses, then you have your unweighted energy carriers, 70 is the total, and this could be 30 units of renewable energy and 80 units of non-renewable energy. With a common renewable energy ratio definition, you are using 30 about on 110 of renewable energy, so you're qualified at 27.3, and that's not enough. But you could say, okay, recovered energy is the same as renewable energy, so I sum up here. So it will be 30 plus 50, which is sustainable, on a total of 160. So it is 50%, which is sustainable. But you could say also that you compare at the energy needs level. So this is fully sustainable. And here only a fraction is sustainable. In this case, the result will be that you have 63% of sustainable energy for this use. And as you can see in this simple example, depending on the conventions, you can change and turn upside down the result. And it's very important that this is very well analyzed and very well understood when regulating energy performance of buildings. And you can avoid all these things, avoiding this kind of indicators or any similar ratio, and keeping in mind that the actual concern is not how much renewable energy we use or how much sustainable energy we use. The problem is how much non-renewable energy we use and how much CO2 we emit. And the rational solution to have a fair evaluation is just check how much CO2 is emitted with the same service. And whatever happens, renewable energy, efficiency, regeneration, they are all evaluated in the same way. And if you fear an excess of installation to be more effective, this could be also another issue. So the life cycle analysis is a correct complement. But we can still also remember that installation costs are indeed a good warning about an excess of expenditure in equipment to get the last point of efficiency. And this concludes my presentation. So we can go to the question time. Thank you.